Now, one of the main reasons that partial derivatives are so useful is that we already know how to calculate them in some sense. They are calculated in the exact same way that we calculate derivatives of functions of a single variable with a slight adjustment to the rules. So when we want to calculate a partial derivative, we do it by treating its own variable normally. So the derivative with respect to x of x is just 1. That's the ordinary derivative. And we say that, well, whenever we take a derivative of one of the other variables that we're keeping constant, we think of those as constants, and so those derivatives are 0. But other than that, we still obey all the same rules for calculating derivatives that we have from single variable calculus. So we still have a product rule, a chain rule, power rule, quotient rule, all the other rules that we have from the classical case. So for example, let's say we wanted to calculate the partial derivatives of this function here, x squared sine y plus y cosine of z. This is a function that takes 3 inputs and produces 1 output. Because it has 3 inputs, it has 3 different partial derivatives. We could calculate the x partial derivative, we could calculate the y partial derivative, or we could calculate the z partial derivative. And when we do that, we get 3 different things that tell us how the function is changing when we change those inputs. So if I calculate the partial derivative of this with respect to x, well, I should first use the sum rule. So let's do this in a little bit more detail. The x derivative of x squared sine y plus y cosine of z. So that's the same thing as, well, I'm allowed to use the addition rule for derivatives. That's a standard rule. So it's the same as the x derivative of the first part plus the x derivative of the second part. And then this second part is y times cos z. That's constant from the eyes of the variable x. It doesn't change when we change x because it only depends on y and z. And this is 0 as a result. Whereas on the other side, again, we're taking the partial derivative of x squared times sine y. Sine y is also a constant from the point of view of x, and so we can pull it out. So this is the same as sine of y times the derivative with respect to x of x squared. And that's a familiar derivative. The derivative of x squared is 2 times x. So this is sine of y times 2x. So this is the formula for the partial derivative with respect to x of this function on top. Similarly, we could go through and we could calculate what the partial derivative with respect to y and the partial derivative with respect to z are. Just for the sake of completeness, the partial derivative with respect to y is going to be x squared cosine y plus cos z. Here we can see the effect of taking the derivative of sine y and leaving the other parts as constants. Whereas if we take the partial derivative with respect to z, the first part is going to go away because x squared sine y doesn't depend on z at all, and we're just going to be left with y times minus sine of z. So that's minus y sine z. So we get 3 different partial derivatives for this function.